For billions of years, a white dwarf is trapped in a stalemate. Gravity pushes in and the electrons inside the star push out. But that balance has a hard limit, 1.44 times the mass of our Sun. The moment the star crosses that line, the weight becomes too much. The electrons give out and the floor drops. The star begins to collapse. If this were a normal star, it would just heat up, expand, and stabilize. But a white dwarf has a broken thermostat. As gravity crushes the star, the immense pressure violently forces the dead carbon to start fusing again. The fire spreads, but the star can't expand to cool itself down. The heat just builds and builds and builds, sparking a runaway thermonuclear chain reaction. It is a planetary-sized fusion bomb. In a matter of seconds, the star consumes itself, blasting its guts, including the iron that now pumps through your heart, out into the universe. Inside every white dwarf, the laws of quantum mechanics stage a silent standoff. Gravity never lets up, squeezing the star's core with the weight of a million Earths. But the electrons, packed tighter than atoms in steel, have a secret weapon: the Pauli exclusion principle. No two electrons can share the same quantum state. It is a cosmic version of rush hour, a quantum traffic jam, where each electron is forced into its own lane, no matter how cramped the space becomes. This pressure has nothing to do with heat. Strip a white dwarf of all warmth, cool it to absolute zero, and the support remains. The star does not collapse because its strength comes from the sheer impossibility of squeezing all those electrons into identical states. It is not thermal motion holding up the star. It is quantum law, etched into the fabric of reality. Here is the twist that defies everyday logic. Add mass to a white dwarf, and it shrinks. More weight means a smaller star. As gravity wins ground, the electrons are forced into higher and higher momentum states, jamming the quantum lanes even tighter. The pressure climbs, but the radius falls. This is the non-relativistic regime, where the pressure scales with density to the 5/3 power, rho to the 5/3. It is a relationship that flips our intuition upside down. A white dwarf is not just a dead star. It is a paradox in plain sight. A stellar corpse held up by the refusal of electrons to share space. And the more mass you add, the more extreme the quantum squeeze becomes. The stalemate holds, but only up to a point. Beyond that, the rules change and the floor drops. Subscribe for the next chapter in the battle between quantum law and gravity. Gravity's pressure keeps rising, but quantum law starts to buckle under the strain. As the mass of a white dwarf creeps higher, the electrons are forced into speeds so extreme that relativity takes hold. The rules of the quantum traffic jam warp. When the Fermi momentum nears the speed of light, when x sub f reaches 1, the electrons cannot push back as hard. The pressure law softens, shifting from a density dependence of the 5/3 power to just 4/3. It is like a steel beam turning to rubber. The star's structure flips from an n equals 3/2 polytrope to an n equals 3, and the equation of state loses its edge. Now gravity's pull and quantum resistance are running neck and neck. This is the moment where the floor drops. No matter how much denser the core gets, the pressure cannot outpace gravity anymore. There is no more room to maneuver, no extra quantum support waiting in the wings. The white dwarf has reached its ultimate limit. In 1930, a 19-year-old named Subrahmanyan Chandrasekhar worked out this cosmic boundary on a notebook while crossing the Indian Ocean. His calculation, scribbled on the deck of the SS Pilsner, gave the number 1.44 times the mass of the Sun. That is not just a line in the sand, it is the razor's edge where a star's fate is decided. Beyond this point, electron degeneracy pressure surrenders. Collapse is no longer a threat, it is a certainty. Only a new kind of quantum force, far more brutal, can take over from here. Subscribe to see where the story of gravity and quantum law goes next. A white dwarf left alone is a cosmic relic, strange, dense, but stable in its quantum deadlock. Catastrophe only enters the picture when a companion star joins the act. In a binary system, the white dwarf becomes a cosmic thief, pulling matter from its neighbor. But the universe is picky. The accretion rate cannot be too fast or too slow. Too much, and the star spits the excess back into space in nova eruptions. Too little and nothing changes. Only in a razor-thin window, just a few millionths of a solar mass per year, does the white dwarf quietly hoard enough material to tip the scales. As mass trickles in, the star's core is squeezed tighter. The central density climbs toward 10 to the 9th grams per cubic centimeter. Temperatures surge, brushing up against 100 million Kelvin. But instead of a sudden blast, the white dwarf enters a long, silent pressure cooker. The simmering phase. For 1,000 to 10,000 years, weak carbon fusion bubbles away in the core. Convection churns the interior, mixing heat and fuel, but never quite breaking the quantum stalemate. Yet there is a hidden drain in this system. The convective Urca cycle quietly siphons energy away, as electron captures and beta decays shuttle neutrinos out of the star. This cooling slows the march to disaster, delaying ignition and stretching the simmering phase. But it cannot hold back gravity forever. The companion keeps feeding, the core grows heavier, and the temperature creeps upward. The white dwarf edges closer to the point where even quantum law cannot save it. Subscribe for the next leap from electron stalemate to the brute force of neutron degeneracy. The moment the core temperature passes 700 million Kelvin, the old rules vanish. Inside this quantum corpse, the thermostat is broken. Heat no longer buys relief. In a living star, a burst of fusion would puff the core outward, cooling it, choking off the fire. Here, degeneracy pressure ignores temperature. The electrons refuse to budge. The star can't expand, can't vent the heat, can't turn down the burn. Carbon fusion doesn't just start, it runs wild. The reaction rate rockets upward, feeding on itself. The temperature soars, but the star stays locked in place, unable to push back. What begins as a spark becomes a runaway. The burning front grows unstable, twisting and writhing through the core in a chaotic, turbulent flame. This is deflagration, a subsonic burn, messy and uneven, carving tunnels of destruction through the stellar interior. But the violence doesn't stop there. In the right conditions, turbulence and pressure spikes force the burning front into a new regime. The deflagration jumps to detonation. The flame front accelerates, slamming outward at speeds up to 20,000 kilometers per second. There is no turning back. The entire star is torn apart in less than a second. No gentle fade, no partial survival, just total obliteration. The white dwarf's quantum stalemate is shattered. All that's left is chaos, energy, and the ashes of a dead star. This is the hinge of fate, the broken thermostat, the runaway. The moment where gravity and quantum law lose their grip. The next chapter belongs to neutron degeneracy, the last barrier before collapse. Subscribe for the final showdown. The star is gone, but the light remains. What you see in the sky after a Type Ia supernova, it is not the blast itself, it is the afterglow of atomic decay. The brilliance that lingers for weeks and months comes from the wreckage, nickel-56 forged in the explosion, unstable and restless, shedding energy as it transforms. In just over 6 days, half of that nickel-56 decays into cobalt-56, and over the next 77 days, cobalt becomes iron. Each step releases gamma rays, flooding the expanding debris with energy and making the supernova visible across galaxies. The initial shockwave is over in seconds, but the radioactive heart keeps beating, its light curve tracing the slow countdown of atomic clocks. This is not just a cosmic spectacle. The iron at the end of that decay chain does not vanish, it drifts out, seeded across the galaxy. Every atom of iron in your blood was born in such a fire, flung from a dead star's final act. The white dwarf's defeat is the universe's gain, scattering the raw material for planets, for life, for the next generation of stars. But when electron degeneracy finally fails, something even stranger waits in the wings. Neutrons take the stage, and a new kind of quantum pressure rises from the ashes. For that story, subscribe and follow the battle into the heart of a neutron star. At 1.44 solar masses, physics flips. The quantum stalemate shatters, the floor drops, and a dead star ignites itself into cosmic detonation. Every heavy element in your body was forged in that runaway moment. Tomorrow, neutron stars test the laws even further. Subscribe to witness where gravity breaks next.